So welcome everybody to this session on the future of climate modelling. It's really great to see so many people here, and I hope you can all keep your cool over the next 90 minutes. This is a really important session because we're talking about a really crucial tool to provide information for the challenge that we are going through, the transition over the next decade and the further decades. So in this session we want to talk about the needs of and requirements for climate modelling, and also delve into some of the priorities that we need to make and choose as we develop those climate models to provide the information that we need, both for the mitigation and adaptation aspects of addressing climate change. I should explain that I'm Peter Stott. I'm from the Met Office, as well as the University of Exeter, and I will be your co-facilitator today alongside our remote chair, Professor Detlev Stammer, Head of Remote Sensing and Assimilation and Director of the Centre for Earth System Research and Sustainability at the University of Hamburg, and also the Chair of the Joint Scientific Committee of the World Climate Research Programme. So before I hand over to Detlev, I just want to say a few brief words about the structure of today's session. First of all, we're going to hear from three speakers for about we're going to hear from three speakers with presentations. We're first of all going to, and this will explore, I think, some of the dimensions to sort of get us started, both internationally and also here in the UK. So we're going to start off with Paul Monks, Chief Scientific Advisor for the Department for Business, Energy and Industrial Strategy at the UK. And he's going to announce the launch of the UK National Climate Sciences Partnership, which is a partnership between the Met Office, national research centres and universities here in the UK to develop further the climate science we need for climate services. We're then going to be followed by Dr. Zudu Segela, Senior Climate Scientist at the IGAD Climate Prediction and Application Centre, Eekpak in Kenya, who will provide us another fascinating perspective. And then we're going to follow that up with Dr. Greg Flato from the Canadian Centre for Climate Modelling and Analysis, and he is Vice Chair of the Intergovernmental Panel on Climate Change. When we've heard from those speakers, we will then proceed to a panel with 5 further speakers, so I'll introduce you to in due course. Without further ado, I'll hand over to Detlev, our remote chair for today, who will provide some further introduction. So over to you, Detlev.
Yeah, thank you very much, Peter, and thanks for this kind introduction. This is a very important session. In fact, we have prepared 2 slides. Peter had now already read part of these slides. To introduce to you the program of today's session. As Peter mentioned, climate modeling is an absolutely important tool to study the climate system, to provide predictions. And I think it's clear to everybody online who is speaking here that without these climate models, we would not have that information that, for instance, the IPCC process or the COP26 used to come to the conclusions that humans are influencing climate in the way that we predict now. And it's now time to, in fact, after the last 30 to 40 years, where in particular the World Climate Research Programme actually had pushed this and developed this tool very much, to think about the future of it. And so this session, this event here is really about thinking forward into the future, and all the keynotes setting the stage, and then the panel discussions afterwards are really addressing the needs for the future of climate modeling, but also addressing the needs of the users and the stakeholders. And so with this, we have a very tight program, and I do not want to be the first running over time, but in fact asking everybody to be on time. I would like to start with the first video message that Peter already introduced. It's from Paul Monks, Chief Scientific Advisor of the Department for Business, Energy and Industrial Strategy of the UK. And I would like to ask now to start this video.
Thank you for inviting me to say a few words on this, the launch of the UK National Climate Science Partnership. Undoubtedly, over the last 40 years, climate science has raised humanity's understanding of the threats of human-made climate change. Now is the time for action. Climate science, in my opinion, is not just about describing the problem, but also about enabling solutions, and we know there is more to do. Knowledge of climate change is increasing exponentially, but so is the threat of climate change itself, particularly from extreme weather. Responses to these threats will need to be informed by the latest knowledge about how the climate system is changing and what will happen next. Many responses, such as flood defences, take time to implement, so it's important we focus on building the science which tells us where we need to build the resilience. To keep our climate change knowledge up to the minute, we need core capabilities to monitor, model and predict how the climate will change, and critically, what this means for people. To do this, we need to monitor the ongoing changes in the climate system and their impacts on nature, on people and on business. Test and improve climate models so that we can be increasingly confident of how fast climate will change in the future. To provide early warning of hazards and high impact changes such as tipping points. To quantify risks and opportunities for businesses exposed to climate change. And to evaluate the benefits and risks associated with specific mitigation and adaptation options. For me, that's important to enable effective and resilient pathways to net zero. We also need to take all this knowledge and deliver it to policymakers and businesses so that they can make the right decisions. Climate scientists should reach out beyond their traditional disciplines to collaborate with experts in many other scientific fields, hydrology, agriculture, economics and human behaviour, but also with practitioners delivering outcomes in policy, planning and business. The UK is in an enviable position upon this. We have a proud reputation as a leader in climate science and its application to policy. We have recognised the need for climate science that addresses real-world problems, the threats to UK prosperity and the security to climate change that poses. Today, I'm really pleased to announce the formation of the UK National Climate Sciences Partnership. It brings together the leading UK climate science capabilities across the UK Met Office, the national research centres and our universities to meet these new needs. The UK National Climate Science Partnership will deliver that climate information that we need for climate solutions. It will also ensure that our climate science capabilities, including capabilities in climate modelling, continue to be world-class and push the frontiers of technological capability. For me in particular though, crucially the UK will play a leading role in developing an end-to-end climate decision value chain that takes the data at one end and the analysis at the other end and all the steps in between to design and assess the required policy options. This will allow a clear line of sight to enable climate science to climate policy, which means that the UK will be better prepared for the climate change which is to come, even as we continue to make the huge strides of our path to net zero. The actual formal launch of the National Climate Science Partnership will take place in 2022. But the key steps now is that the partners will come together with new commitment and a new vision to deliver this essential UK capability. Thank you very much.
Thank you. And this really set the stage for, in fact, the expectations that are being set in climate models, in particular in the future. And just for the audience, we will continue now without any questions, but we will actually, after the panel members had their intervention, we will give a 30-minute opportunity for asking questions. So with this, we would now continue with the second keynote. It is given by Zido Zegele. He is the head of the IPCC Climate Modeling Group. IPCC stands for Climate Prediction and Application Center in Africa. And Zido Zegele is on the floor in Glasgow. And yes, I see him. And so please, Zido, go ahead.
Thank you very much. Yes. Thank you very much. I have a few slides to show, and Eekpak has a certain modeling capability. This was first installed or procured from FCDO. So this is used primarily for resilient and adaptation and for a number of projects. What I am showing here is what we use the regional climate modeling for. So we downscale to the Greater Horn of Africa region. We use the dynamical downscaling for short-range forecasts from weekly to monthly to seasonal forecasting. In a short-range forecast for 3-day forecast, it's primarily on tracking the tropical cyclones that form over the Indian Ocean during September, October, November, December, as well as during the spring season, Northern Hemisphere spring, and this shows some of the tropical cyclones that were simulated with the 3-day advance forecast. Some of them have caused quite havoc over Somalia, for example, the Geti. So this is quite interesting and dynamic tool for early warning purposes. The other is for a weekly forecast. This is again, we forecast extreme rainfall. If rainfall exceeds the 90 percentile or 95 percentile or 99 percentile, so we give emphasis that, and we use that for early warning activities. And usually such forecasts are quite accurate. For example, what we see here is a weekly forecast given on the 4th, and during October, when the intertropical convergence zone pushed much further south, we see unusual rain over the Djibouti area. So this is quite a very useful product for early warning purposes. Another use is on seasonal forecasting. For this, what we use it for is to assess what a forthcoming season, a month or two beforehand, how it look like, especially in terms of the onset, and if there are any dry spell in the coming season. Usually we define the dry spell in terms of the maximum consecutive days, or we can define it in terms of the frequency of dry spells, or the maximum ever within that season. And currently we don't have reforecast. We are working on reforecast because that is a lot of data to work on. But we have reanalysis driven analysis which we compare it to, and we show anomalies, which helps in comparing with past seasons. Another thing is in terms of statistical forecasting. So we do downscale a number of GCMs from global producing centers, and we statistically downscale. We provide probabilities, rainfall probabilities for a specified region or zone. We supplement that with SCPI forecast. Currently, with some projects going on, we are developing the soil moisture forecast and also crop yield forecast. This is related with the Comfort project. Down to Earth is using seasonal forecast to assess or to forecast stream flows or groundwater and also surface water. So we found these products quite useful. Lastly, I just want to show we implemented objective forecasting since May 2019. So we removed the subjectivity in forecasting, and we assessed the forecast skill objectively as well. And so far, except a few seasons where there were only about 40% performance. In some season it goes up to 85% and more. And there are some rooms to for improvement. Thank you very much.
Yes, thank you very much. Very nice talk. This was, in fact, quite on time, and so we can continue now with the next keynote speaker. This is Greg Flatto. Greg Flatto is a scientist at the Climate Research Division of Environment Canada, And he is in particular here also in his capacity as vice chair of the Working Group 1 of IPCC. So Greg, you in fact have now, if you like, a few more minutes to speak, and please go ahead.
Thank you very much, Detlef. I appreciate the introduction, and I appreciate the opportunity to speak to you here today. If we could start with the slide presentation.
We need the Future of Climate Modeling presentation from Greg Flatto. By the way, the person on the screen in Glasgow is not Greg Flatto, it's actually Rick Spinrad. So now we have Greg Flatto on the screen, but we also need his presentation.
Although Rick is obviously better dressed and better looking than I. There we go.
Here
okay.
it comes. Okay, great. Go ahead.
Thank you. All right. Thank you. And I'll reclaim my time later. So this, if we can go to the next slide, please. All right. So I'm going to talk about global climate models and kind of the future of climate modeling from my perspective. I thought I would just take a minute at the beginning here, just for those who are watching this and maybe watching it later, to just say a little bit about what these global climate models are, how they're constructed, and how we use them. So just to be clear, what we're talking about here are computer simulations, that is computer programs that represent this coupled complex Earth system. They divide up the planet into little boxes in which we do these calculations, and the size of those little boxes that you kind of see schematically in the middle of the figure determines the level of detail that we can simulate with these models. The models represent processes in the atmosphere, in the ocean, the land surface, the cryosphere, that is the frozen parts of the planet, the sea ice and glaciers and ice sheets, terrestrial and ocean ecosystems, which are important for the carbon cycle, and some other biogeochemical cycles like that involving sulfur and sulfate aerosols, the ozone in the stratosphere, and so on. So they're very complicated models that are based on physics, physical understanding, and on observationally based representations of many of these processes. So if we go to the next slide, please. These computer models require computers, obviously, to run them on. They require very large supercomputers, in fact. And the picture on the bottom there just shows one supercomputing facility in Barcelona. I love this picture because it's got to be one of the most photogenic supercomputing facilities in the world. But we require these large computing systems to run these models, and the output from these models provides scientific understanding. The analysis of these model results allow us to understand how the climate system functions, how it has changed in the past, why it has changed in the past, and more importantly, they allow us to make quantitative projections and predictions of future climate and various aspects of the future climate, including climate extremes. They also allow us to make estimates of very hard to observe quantities because they are a fully coupled system that does have the representation of the physics we understand in them. We can make estimates of exchanges of carbon between the atmosphere and the land, or the atmosphere and the ocean, things that are difficult to observe, and then can be tested against observations to validate these. So if we go to the next slide, please. So there are many modeling centers around the world that develop these kind of coupled climate system models, Earth system models. The World Climate Research Program has a long-standing effort to facilitate cooperation and coordination amongst these modeling centers, something called the Coupled Model Intercomparison Project, which is now just completing its 6th phase, so it's been around for a long time. What this is a way of providing a standardized set of model experiments that groups around the world can conduct, a standardized set of forcings that go into these models, that is changing greenhouse gases and so on, a standardized way of taking the output from these models, putting it into a common format and distributing it for users around the world. That includes practitioners, other researchers, and assessment activities like the IPCC. So if I go to the next slide, please. I have a couple of figures now that show results from the most recent IPCC assessment, just to illustrate this and illustrate the importance of these models in the IPCC assessment process. This is a figure that just shows global mean surface air temperature. The observed value is shown in that dark black line, covers the time period from 1850 to the present. And each of the individual colored lines represent the result from an individual model or a particular configuration of one of these individual models. And you see that there are lots of models that contributed to this. There's a spread amongst them, which allows us to ask questions about uncertainty in these modeling systems, allows us to ask questions about internal variability, natural variability in the climate system, so that we can ask how is the signal that we see, that warming signal, how is that different from what would be expected from internal variability? It also allows us to ask how well these models perform against a range of observations. So they simulate lots of things, not just temperature, of course, but precipitation and cloud amount and ocean circulation and sea ice amount. And we can ask, how well do these models reproduce the historical period? And by asking that question, then we can ask, how much confidence should we have in their future projections? So if I go to the next slide, I give you just an example. This is a little bit complicated figure, but it also comes from the most recent assessment. And one of the assessment statements made in Chapter 3, which my colleague Veronica Hiring was the coordinating lead author of, is that these models have gotten better over time. And that's an important measure of the progress that has been made in Earth system modeling. This figure shows for different periods of the CMAP effort, CMAP 3, CMAP 5, and CMAP 6. So this represents almost 20 years of evolution of these modeling systems for a number of quantities. And I apologize, you probably can't see that across the bottom, but there are things like temperature and precipitation and sea level pressure and wind and humidity and various things. And the little colored dots indicate the correlation between the modeled version of those quantities and the observed version of those quantities. And the green is the oldest set of models, the blue is one from about 10 years ago, and the red is the most current set of models. And in all cases, you see that this progress of the red results being closer to 1, that is a perfect correlation, than the older one. So in every quantity that you look at, there is progress being made. There's still a range across these models, but the models are slowly but surely getting better. If we go to the next slide, this allows us to have some confidence in the results that we get from these models for the future, where of course we can't evaluate their skill, at least not until much further into the future. So the way that we use these models is to take different scenarios of emissions of greenhouse gases, of aerosols, of other things, land use change, put that into the model and ask, how does the climate change in response to those different scenarios? So on the left is a set of 5 illustrative scenarios that were used in the IPCC assessment report. And on the right is the future projections for each of those scenarios from this large collection of models, in this case showing global surface temperature over in the future. And so the ability to evaluate these models based on their past performance helps us to have some confidence in their projection of the future. All right, if I go to the next slide, now I have just 3 quick slides on looking forward here. And one of the things is that in the last IPCC report, we introduced this terminology of climatic impact drivers, that is, changes in the physical system that affect society or ecosystems And many of these climatic impact drivers result from small scale, short term things, extreme events like extreme heat waves or extreme precipitation that causes flooding, those kind of things. And so that puts a demand on these modeling systems to be able to provide more detail, more fine-grained detail in these simulations. And modeling centers around the world are working progressively to improve this kind of representation and be able to then say something not only about the near-term predictions of these extreme events that the previous speaker was talking about, but to say something about how the statistics of these extreme events will change well into the future. So how does the risk of an extreme precipitation event in your region, or an extreme drought, or an extreme heat wave, or extreme sea level rise, how might that change in the future under these different scenarios? So that's one area in which modeling systems are working towards. If I go to the next slide, there's, in order to take the output from these models and make use of it, we have to increasingly transform the model output into, well, we have to increasingly include things in the models that are relevant for the kind of decisions that have to be made. And that it might involve better representation of the way that natural systems function, ecosystems in different places at smaller scales, and the way that human systems function, the way that society operates, the way that energy is produced and consumed, and so on. And that would allow us to ask more directly questions about how changes that we make, both intentional mitigation efforts or adaptation efforts, how that would feed back on the climate system by changing the way that the land is covered. If we introduce bioenergy with carbon capture and storage, for example, that changes the way our agricultural systems look, and that would have feedbacks on the water cycle, the energy cycle, and ultimately the climate. So there's an opportunity there to build more of that in. And if I go to the next slide, there's a further opportunity to take the output from these models and transform them more directly into products and services, information that really allows action-oriented decision-making, that supports planning, that supports risk reduction, and so on. So there's many opportunities there, and the previous speaker talked about that on the basis of shorter-term seasonal predictions, but that also applies to longer time scales. And then finally, just the last slide, some closing thoughts here. CMAP, this coupled model intercomparison project that's coordinated by the World Climate Research Program, really is a stellar example, in my view, of the benefits of international collaboration and coordination across institutions to produce a suite of output that is usable by a whole range of scientists, practitioners, decision makers, and others. So I think that's something that we should build upon. There are many opportunities to do better, of course, to bring in local and regional expertise into not only the modeling effort, but the effort to take the model output and make it more usable. We have to continue to stimulate model development and improvement if we want to meet the future demands for climate information. And that necessarily means more investment in education, in scientific capacity, enhanced computing facilities, more effective data storage, dissemination, ability to visualize this output and turn it into things that people can understand and make use of. And then finally, the IPCC assessments, like the 6th assessment that was just released, reveal gaps and deficiencies in the climate modeling area as well as others. And that allows us to then look at that and plan for the future. And the WCRP is in the process of looking at how it might reorganize itself and recommit itself to improving climate science in the future. And so I think we have a lot of opportunities here wherein we could mobilize resources and expand the community to build on the successes that we already have. So I'll stop there. Thanks very much.
Thank you very, very much, Greg. And yeah, right on time. And it is true that this international coordination is really important. And to some extent, it is an infrastructure that we are talking about here that had to be built up in the beginning and now has to be moved forward on a scale that is by far too large. And in fact, it can be tackled by individual institutions or nations, and I think climate modeling is one of these very complex elements. And with this, we do close now the keynote part and move forward into our panel part, where we basically have now a few experts, first of all, giving us an intervention by each of them, and then be ready to answer questions from the floor. And this is where, Peter, we have to work together how to do this. And the first expert is Albert Klein-Tank. He is, in fact, the director of the UK Met Office Hadley Centre for Climate Science and Services. And Albert, please go ahead. And you are on the floor in Glasgow.
Yes, I am. Thank you very much for the opportunity to speak on this topic, which is a huge topic, the future of climate modeling, I would say. So I'll only have time for a few comments. First of all, I'd like to start with the changing requirements, and Greg already touched upon this. I think it is clear, well, the Hadley Centre is in the business of climate modeling for over 30 years, and you really do see the requirements changing from the models, really a shift from defining the problem to enabling solutions, of course supporting mitigation and adaptation action. I won't provide examples. You've heard many in the previous presentations. But clearly, from my perspective, the science of climate modeling in that respect is not done. I don't say that it shouldn't change, so it might change, and I'll come to suggestions for that as well. So I think it's still necessary to really increase the understanding of the basic mechanisms and the changes in both the models and the observations. And that is crucial for these models to remain valid for the supporting adaptation and mitigation. First of all, let me touch on the topic of moving towards more multidisciplinary approach. And I think Paul Monks, in his presentation and his announcement of this new partnership in the UK, he was emphasizing this multidisciplinarity. I don't know even if that's an English word, but okay. So he was emphasizing that, and I think it is really important from my perspective as well. Climate scientists, and we've heard it before, must really collaborate with experts in many other fields. Hydrology, agriculture, economics. There was a session before this on finance, so the financial sector. That is really crucial. And I think the partnership is our solution, or not a solution, but our initiative in the UK to make this happen at a national scale. I think many other countries have this partially or have initiative in the same direction, and we can learn from each other in that respect. It is really a partnership about multidisciplinarity, but it's also a partnership to join up the modeling capabilities and the observational capabilities. Too often these two are separate domains, more or less, and we should join them more together. And this is really crucial if we want climate models which are evaluated and which are take the observational evidence together to inform the action on mitigation and adaptation. The third topic I want to touch on: are we really on track? Are we making progress with climate modeling? I think there is lots of developments, exciting developments in the modeling, which I will briefly mention. So increased resolution, Greg showed a very good example. So that means that we can, with the generation models, improve the global water cycle, better prediction of storms, so crucial for extreme events like Greg was already mentioning. I think another example is he also mentioned the Earth system model, so complexity in the models. For instance, modeling the ice sheets, crucial for sea level rise and for future climate. Definitely something we need to bring in as well. And in the seasonal forecast, one of the crucial aspects is the ensembles. So we want to know how certain are we about the future. So the number of simulations we can provide, also crucial. What for me is a difficulty leading such a center is we cannot do everything. And I think in every center that will be a crucial question. Where do we focus? Where do we set the priorities? We have a limited computing resource, but maybe even more important, we have a limited human resource. It's very important that we aim to develop, I would say, evidence-based approaches to how our future path of where we navigate between resolution, ensemble size, and process complexity. Another topic, if I may, for a few minutes, working with the new technology and the new supercomputers. And the Met Office, I think some of you will have heard, the Met Office has set up a partnership with Microsoft for our new next generation supercomputers. That will mean a lot of additional work to make these computer models, these climate models, fit for purpose and fit for the future generation of supercomputers. And that's a lot of technical work. But as Peter Stott reminded me yesterday, let's not forget about the thinking and the developing the science alongside. So it should not only be a technical exercise, these new supercomputer and exascale modeling systems. Maybe one thing to mention as well is digital twins. I think machine learning and artificial intelligence was mentioned earlier. Digital twins of the Earth, that's the new, the new topic where a lot of people are very excited about, including myself, because it really fulfills part of these ultra high resolution desires and requirements for the models. And like the EU Destination Earth initiative is really focusing on that. But I think for me, it should definitely go beyond traditional climate modeling, because we already do a lot of these very high resolution modeling. Greg showed an example. We have in the UK, we have examples of very high resolution global models, regional models over large domains. So we do see that they bring more processes, the convection permitting models in particular. They bring in more processes, they increase the risk assessment of extreme events in particular. But I don't see this digital twin development, I don't see it really solving all the problems in the next 10 years. The action we need to take is in the next 10 years mainly. So we need a hierarchy of different climate models, more complex, less complex. For instance, Earth system models linked to integrated assessment models for exploring the mitigation options, supporting carbon budget estimates, etc. It is really about this hierarchy of models which is crucial, I think. And where I see the added value of digital twins is when we link the more traditional climate models with the other domains. If you data from other domains and data from vulnerability and data from exposure, and if we are able to link this together, there's where we can use machine learning and AI to do this. And that's where digital twins really have an added value in my perspective. And the very final point is on CMAP, because CMAP is debated a lot, and Greg mentioned this model intercomparison initiative. One aspect for me, which is also very important, it is a benchmark for the different modeling centers, but maybe even more important, this is a system or a way to engage scientists from across the world to engage in the modeling work and in the model evaluation. And I think that you cannot underestimate the benefit also to developing countries and scientists in these countries to participate in the global community. And that's a really very good entrance to this. Good. One quote.
You need to come to a close.
Yeah, I come to a close. I come to a close with someone from the Met Office Center you know very well, Kirsten. She was telling me, please do emphasize that we need to bring the different data sets together from the high resolution models, from the lower resolution Earth system models. This is really the crucial aspect of a future of CMAP. How do we do this? How do we bring these sources together? And international collaboration is essential in that respect. And I'll leave it here.
Thank you very much. All very valid points, and I do want to remember that WCIP is in fact opening or entering a new activity. It's called Digital Earth, which is a digital twin, but it's not just modeling, it's also observations. And of course, bringing models and observations close together is absolutely critical in this. But all good points. We have to move forward, and sticking everybody to 5 minutes. I would like to introduce now the next panelist, which is Kirsten Findell. Kirsten is from GFDL, a NOAA lab, and I thought, in fact, this is absolutely relevant for today's session. This NOAA lab was one developing the first climate models, and we all know that recently climate science received 2 Nobel Prizes. One actually went to Suki Manabi, to other Klaus Hasselmann in Hamburg. Both were in fact essential in developing climate models, and we all benefit now from this. And so with this Kirsten, please go ahead with your 5 minutes.
Thank you, Detlef. Excuse me. Thank you, Detlef. I think that's a really important point you make there. When we think about how far climate modeling has come over the past 6 decades, it's really quite spectacular. When you think about those first models that Suki used 6 decades ago, they were one-dimensional, single-column atmospheric model. And now here we are with these complex Earth system models of today. And I'm sure that in the future, climate models, as previous speakers have alluded to, that will certainly be more complex and they'll be run at higher resolution, but they'll continue to serve that same valuable purpose that they have served through these decades, because climate models are our single best tool for understanding the Earth system. And they're particularly valuable for giving us a sense of what our future trajectories might look like, where we don't have observations, obviously. So as Detlef mentioned, at the Geophysical Fluid Dynamics Laboratory, or GFDL, where I've worked, we've been at the edges of this climate science for more than 60 years. And GFDL is one of many NOAA labs, the National Oceanic and Atmospheric Administration in the United States. And we're lucky enough, at the end of this panel, we'll also have Dr. Rick Spinrad, who's our NOAA administrator on the panel. And I do, again, want to emphasize what Detlef mentioned about Suki Manabe being awarded the Nobel Prize in Physics for the foundational climate work that he performed while he was a scientist at GFDL. And I think that Suki really brought, he helped develop the practices that are still at the heart of what we do today, both at GFDL and at climate modeling centers all over the world. We combine model development with theory and observations, and with targeted experiments and analyses to improve our full understanding of the Earth's climate system. So looking to the future, the next decade or two, as alluded to by previous speakers, the next decade or two really could be revolutionary for climate science. But computing power is obviously a constraint. And I really appreciate what the previous speaker mentioned, that human resources are also a constraint to consider. But when we think about what climate models could have, they could be run at high enough resolutions to depict small-scale cloud features in the atmosphere, as well as turbulent eddies in the ocean. We could have suites of large ensembles of simulations just be the norm. And models could certainly include complex representations of a host of new physical processes, particularly, I think, at the interface between model components. I'm thinking of things like how coastal groundwater systems could be modeled to respond to rising seas, and how the atmospheric boundary layer could respond to subgrid heterogeneity at the land surface. And importantly, climate models of the future could also include coupled representations of human involvement in the climate system, including management of the hydrologic cycles, such as dams or reservoirs or groundwater extraction. And I can even picture them including physical structures designed to hold back rising seas from vulnerable low-lying coastal regions. So I think the possibilities are vast. We can also imagine, forestry or crop or agricultural management practices being incorporated into Earth system models rather than being run as separate offline entities forced by climate model output. So, but as previous speakers have mentioned, with these expanded capabilities come the opportunity for much deeper understanding of the climate system, but we can't accomplish all of these things at once. So while we need to make progress on all of these fronts, the opportunity for transformational change in scientific understanding, I think it might be greatest for those timescales that are between traditional weather prediction models on one hand and century timescale climate models on the other. So in that in-between space where we think about seasonal to decadal prediction systems, these provide the climate science community with a new opportunity to develop predictions and projections on timescales that were previously inaccessible due to small signals being swamped by large amounts of noisy internal variability in the system. However, recent advances with large ensembles of simulations, which have been alluded to previously, particularly those with observationally informed data assimilation systems, those types of systems suggest that an operational capability for multi-annual to decadal explanation and attribution of Earth system change is within reach. And this is, in fact, the goal of one of the World Climate Research Programme's new lighthouse activities, the activity dedicated to explaining and predicting Earth system change. Our goal within this lighthouse activity is to develop an operational capability for understanding and attributing Earth system change on regional to global spatial scales and at multi-annual to decadal timescales. So as part of this activity, we envision a tighter integration between coupling and observational, between observational and modeling systems, where observations are used to confront and expose weaknesses in the models as they are today, and where models are also used to expose gaps in observational networks, and also to optimize placement of observational stations where perhaps you might need more information to adequately feed the climate models. So we also aim to understand how large-scale changes in the Earth system, how they develop and propagate, and how these changes could impact risks of hazards like tropical cyclones or multi-year droughts. And additionally, and importantly, I think, we want to determine what physical signs might be robust early indicators of such events. So all of this requires a comprehensive prediction system comprised of ensembles of hindcasts to help understand, explain, and attribute past changes in the climate record, as well as ensembles of forecasts to help provide probabilistically sound projections of our near-term climate. So we have a capability like this at GFDL, but given the enormity of this task, the international collaboration that was just alluded to, and the international collaboration that I think this WCRP activity gives us a platform to pull in efforts from the whole international climate science community. And I think that's really, really important. So now I'd just like to make one final point, and that is that I think these climate models of the future need to be powered by renewable energy. And I say that from my perspective, both as a climate scientist, but also as a mother. I think the climate science community must not add to the problems that will be passed down to future generations. We should be leading the way in fueling our efforts with renewable resources. So my vision of climate modeling of the future includes extensive solar arrays and wind turbines at climate modeling centers all around the world, so that we could use the gift of the sun's energy to better understand and predict the behavior of the whole Earth system.
All right, thank you very much, Kirsten. What I actually did not mention before is that Kirsten is a co-chair of one of WCRP's new lighthouse activities. In fact, she gave you already the title. And with this, in fact, it's a very good opportunity to hand over now to the next person, which is Rowan Sutton, the second co-chair of the same lighthouse activity. And so, Rowan, I'm now very curious to hear what you are saying.
Thank you very much, Detlev. Coming at this stage in the proceedings, not surprisingly, quite a few of the points I would like to make will reinforce points that have already been made, but I would like to sort of highlight a few perhaps distinctive aspects as well. So this conference, this whole COP26, is all about high ambition. So I think a critical question for this session is, what does high ambition look like for the future of climate models? What can we do to maximize the contributions of climate models and climate science to addressing the climate emergency? And this is all about picking priorities, as Albert highlighted. And some of these choices around priorities are not easy. So I guess I'd like to share my personal views about what some of the right priorities might be. So with that context, I'd like to make three points. Firstly, I think we need to move away from the idea that all climate models are useful for all problems. We need to be more focused than that. We need to focus on specific user needs and what are the right tools and strategies to address those user needs, and what are the key scientific uncertainties that are relevant to the decisions of particular users. So in broad terms, I think we know what the user needs are when we think about both adaptation and mitigation. Essentially, the needs are firstly for risk assessment, and particularly assessment of high impact risks. Secondly, for early warning, as we heard about from the many examples from Eekpak. And thirdly is the evaluation of options, adaptation options, mitigation options. Are these options likely to work? Will they deliver what we would hope? So these are the user needs. We kind of know this. What are the key uncertainties? Well, the big cross-cutting uncertainty is what is the climate system's response to greenhouse gas forcing? Now, we know a lot about this, but we don't know enough. And we have to say this very, very clearly. We know a lot, but we don't know enough. In particular, we don't know enough about the changes on regional scales in atmosphere and ocean circulation and changes in extreme events that are critical for hazards. So this is a key uncertainty that is of cross-cutting relevance to almost all the user needs. So we've got to target that and do what we can to accelerate progress as much as possible. So just to sort of elaborate a little bit further, for adaptation, of course, what we care about is local change particularly, and extreme events, and those are often conditioned by atmosphere circulation, ocean circulation. For mitigation, we care particularly about global change, the possibility of nonlinear changes, tipping points, the possibility of new feedbacks that we haven't understood. So these are some of the key aspects we need to advance understanding of. So what strategies and priorities should we have? So I would like to highlight four priorities. Firstly is the challenge of global storm resolving models, which many people have highlighted. So our current models do not resolve convection in the atmosphere, which is a critical process on kilometre scales, and it interacts with all other scales. Similarly, they do not resolve ocean eddies and boundary currents adequately. And these two weaknesses together come with big uncertainties for our predictions about regional and local scales. So we need to develop storm resolving global models. And that's a grand challenge, and it's incredibly important. It will require international collaboration. It's very, very computationally demanding. So we need to do that. That's one strand. But we have to also be very clear that this isn't a silver bullet. In particular, it's not a silver bullet because it's so computationally demanding. We will not be able to do the large ensembles that we heard about from Greg, for example, and Albert, that we need to quantify risks at the kind of resolutions that we're talking about for storm resolving models. We won't be able to do that anytime soon. So global storm resolving models, yes, but in addition, we need large ensembles of essentially physical climate models to quantify hazards and risks. And that does involve some compromises between resolution and ensemble size. But that's the second strand that we need. Thirdly, we continue to need global Earth system models to understand the full range of feedbacks in the system, and crucially to evaluate mitigation options, for example, around land use change. What feedbacks might they trigger? Could they really work? Or changes in short-lived climate forces. These global Earth system models are the only tools we have to explore some of the potential feedbacks and tipping points, and we need to continue to develop those. So that's the third strand. And the last one is, if you like, the big cross-cutting one, which is what Kirsten focused on, which is the set of strategies around bringing together observations and models in order to explain changes that we observe, in order to improve risk assessments, and to improve predictions. So this is central to the Lighthouse activity that Kirsten talked about and that she and I co-chair. And also within that space of bringing together observations and models are, of course, the digital twin type capabilities that Albert talked about. And indeed, this whole area of bringing together observations and models is central to the National Climate Science Partnership that Paul Monks announced for the UK at the beginning of this session. So those are the four strands that I would say we should prioritise going forward. And I would encourage all organisations to actually, pick some focused areas here and say which are the ones that particular organisations and indeed nations are going to specialise on, so that collectively and internationally we can make the most rapid progress possible. Thank you.
Thank you very much, Rowan. And with this, we turn over to Veronica Hiring. Veronica was already introduced as a coordinating lead author of Chapter 3 of the last, or the 6th assessment report, Working Group 1. Of course, as you can see from her T-shirt, Veronica is very deeply, or was very deeply involved, still is, in CMAP. And so with this, over to you, Veronica.
Yeah, thanks very much. It's a pleasure to speak here today. So I will take the coupled model into comparison project CMAP that you can see here on my T-shirt. Actually, I recognize my it's quite dark here, so you can't see anything. Actually, one moment. It's probably not getting any better if I do this. All right, so you will have to live with my shade. Anyway, here's my T-shirt. So CMAP is a project of the World Climate Research Program, WCP, that started already over 25 years ago, only with the coordination of a handful of early generation atmospheric models at that time. And these were quite simple with coupled dynamic ocean, a simple land surface, and thermodynamic sea ice. And over the time, CMAP has evolved over 6 phases now into a major international multimodal research activity that has not only introduced a new era to climate science, but has also become a central element of climate change assessment reports, including the supporting of the IPCC reports from the very start. And across the years, when you look at this, the climate models have continued to be developed, and the number of CMAP models has substantially increased. And Greg has already said, and I fully support the value we have through CMAP, through the international collaboration across the entire world, which is really very valuable, but also the benchmarking of the models against observations. In the past decade, then, many of the models have been extended into Earth system models that, in addition to the physical climate, also assimilate interactive carbon and other biogeochemical cycles. I think this is an important development that has to continue to fully represent the questions we will have to answer in climate modeling. And now when we look at the current generation, we see that we already have increased spatial resolution, improved physical process representation, and additional Earth system processes and components such as sea ice sheets in these models. Now, as Greg has already mentioned, we also have an increasing wealth of observations, which is great to monitor the climate system, but which we can also use to evaluate these models, and that's a very important activity. And here we can show that indeed the simulation of the recent mean climate has improved in the current generation, and that these models are really impressive in their ability to simulate large-scale indicators of climate change. But nevertheless, we have uncertainties in climate projections that have also been partly addressed by the previous speakers. So one of the most notable one is the range of simulated effective climate sensitivity, which is for larger ensembles. So we will need to continue to lead. Simulations can be used machine learning based parameterizations that are then incorporated into the core scale Earth system model and hopefully represent, for example, a better cloud there. And the key goal would be to a hybrid model that maintains physical consistency and also realistically extrapolates to unseen climate regimes. So despite the remaining uncertainties which the climate modeling community will continue to work on, I want to close by saying that we do not have a knowledge deficit. We know that immediate action is required. And it is unequivocal that human influence has warmed the atmosphere, ocean and land. It's widespread and rapid changes we see in the Earth system that have occurred and are unprecedented over thousands of years. And the IPCC 6 assessment report of Working Group 1 also clearly shows that unless there are immediate, rapid and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees will be beyond reach. So I personally really hope that the science is heard at this conference and that immediate and sustainable measures will be agreed. Thank you.
Thank you, Veronica. And before we continue, can actually I get a response from Glasgow, from the floor, that everything is on track? Because in between the picture was black, and I'm not sure how much of Veronica's speech you heard.
We did hear Veronica's presentation. We lost a bit of video halfway through, but we're now back on track, Detlef, right, so we can continue with the event.
Thank you very much. That is good to hear. And with this, I would like to turn over to Rick Spinrad. who since recently, not too long, I'm not sure exactly how long, is the administrator of NOAA, and of course a great scientist. Rick, we are eager to hear your views.
Thank you, Detlef, and I am honored to be invited to sit on this panel with such an esteemed group of scientists. I should also add, I look forward to joining many of you in Glasgow later this week. I will be part of the U.S. delegation flying out tomorrow. And I'd like to use this session to echo some of the thoughts we've already heard and also make a couple of announcements about some U.S. deliverables. So let me start by just introducing some of the audience to the breadth of NOAA's modeling portfolio, and it really reflects the span of our mission from the surface of the sun to the depths of the ocean. But probably more importantly and relevant to this particular discussion is the responsibilities that we have on an operational sense and a research sense for addressing the full spectrum of climate impacts, which for us means everything from looking at the consequences of decarbonization as related to atmospheric phenomena such as intensity and frequency of tropical storms to even things like impacts on the diversity and geographic distribution of economically critical fisheries species. So I'd like to frame my comments along three fundamental themes. The first is knowing what the needs are. We've got to understand what the climate modeling needs are of the communities we are serving in terms of the projections and predictions and forecasts we'll be developing. And fortunately, we have a number of tools at our disposal, if you will. With a particular emphasis on the ocean's role in climate, we look to things like the Intergovernmental Oceanographic Commission's report from last April on integrating ocean carbon research and how ocean carbon knowledge can help fulfill some of the observational needs for the next decade. And it talks specifically about carbon research and monitoring to provide climate products to policymakers. In that regard, a deliverable that I want to announce here is that in order to advance the research agenda envisioned in that report, NOAA is pleased to announce the establishment of a global operational surface ocean carbon dioxide network to quantify ocean CO2 uptake on seasonal timescales in near real time, which is critical for decision making and policy assessments, as I'm sure the audience can infer. Similarly, there's another deliverable we'd like to share with you, and that is the complement to that first deliverable, which is a new tool within the World Ocean Database to increase the accessibility, usability, and aggregation of global ocean carbon data that NOAA and the IOC's International Oceanographic Data Exchange are undertaking. So between the data access and the carbon dioxide network, we should be able to contribute strongly in terms of the ocean's role in climate change. And when we're discussing modeling needs, we also need to focus on the end users and the customers, which means identifying climate vulnerabilities. And there's a strong equity lens in doing that. Make sure we're engaging with the communities that have historically been underserved and are most vulnerable and are on the front lines of climate impacts. So that first theme is really about developing knowledge. The second is really about developing the capability to deliver. Best models in the world aren't enough. We need to make sure that the deliverables are usable, which means a lot of co-development. It means using traditional ecological knowledge. It means understanding the challenges of things like coastal resilience. And so the third deliverable I'd like to announce is that NOAA, in conjunction with our partners at the U.S. Geological Survey, the Environmental Prediction Agency, NASA, the Army Corps of Engineers, and the Federal Emergency Managers Administration, are engaging in some scientific collaboration to enhance the sea level rise state of science by providing some foundational scientific input for the United States' 5th National Climate Assessment, and really advancing coastal resilience relevant to planning, emergency planning, and design of coastal infrastructure. The third theme is about communicating the uncertainty. And I echo so many of the great comments that were made specifically by Greg and Veronica. I mean, uncertainty is an inherent part of all of the predictions and projections, and understanding that is going to be an important tool in how we make information available to users. In discussing this, for example, with the reinsurance industry, they talk about transferring risk by understanding stakeholder liabilities. And the role of CMAP, as we just heard from Veronica, is critical. We've got to improve quantification of uncertainty in the climate models and projections. The focus that I'd like to emphasize in that regard is, as you heard from several speakers, on regional variability. Whether it's sea level rise, magnitude, and being so dissimilar at various locations, or as Rowan alluded to, the storm resolving local models. And communicating these kinds of uncertainties and variabilities is particularly important. Kirsten emphasized the role of multi-models and ensembles. I can't emphasize strongly enough that particular aspect of communication is going to be important. And I second Veronica's invoking machine learning as a key tool. We have to more accurately quantify uncertainty in the initial estimates of the model system. We've got to employ improved, more physically based methods for quantifying the growth of forecast uncertainty due to model imperfections. And we need to utilize statistical post-processing methods to improve the skill and the reliability of the ensemble model output. So in closing, we look at this as a three-stage effort. One is in building knowledge, one is in building capability, and the final piece is in communicating uncertainty, and I should say communicating certainty where we have it. Thank you.
Thank you very much. So this concludes our intervention part of the panel, the discussion. And we now have between 15 and 20 minutes to answer questions, and this is a little experiment. So we have to work together here, and I think we start with questions from the floor in Glasgow, and you would actually need to take the questions and maybe speak them loud. And then we see which panel member wants to answer.
Yep, that sounds excellent, Detlef. So I will take the lead in transporting the microphone around the room and taking questions. And then, Detlef, you can take the lead in choosing the panel member. So let me just put my mask on for a second. There we go. Right, who have we got? Let's go over there. Sorry?
Hello. Yes, my name is Rosa Galvez, and I am a senator from the Canadian Parliament. And but I'm also a researcher. I'm also a professor in civil engineer, where my colleagues in hydraulics does some of the models that you have shown. And I am thrown in between two parts. On one hand, my science background and my desire to attain certainty to unequivocally said that planet warming is due to human activities, and also as my role as a politician, where I don't see that what you are showing with your data are being used as you're saying that it should be used. So, there is an Exxon model in the 70s that said that the planet was warming. Then IPCC has been founded in 1988, and the colleague said that it's been 60 years we've been working on this. I really, really need to know how you are transferring this to the stakeholders. I know the oceans, I know the agriculture, but we need to send it to banks, to insurers, to politicians. And so communicating uncertainty, yes, but communicating certainty. It is becoming, because we are in code red. You said it in your report. Thank you.
Yeah, thank you very much. This is an excellent question. And in fact, the first report on the expected impact of humans was from '79. And in fact, since Arrhenius, we know about this. And it is, in fact, a very important and interesting question. Why is it so difficult to get actually action happening? And so of course, Rick, I can turn this over to you, but maybe Rick starts and then everybody else can join in.
So, yeah, thank you, Senator, for that very important question. I think it's one that we all struggle with. I can tell you that my own personal philosophy, which I'm trying to build through the mechanism of the U.S. federal government, is twofold. One is we need to get out more. And when I say we, I mean the technical community. And when I say get out more, I mean reach to some of the communities you alluded to. For example, I have now started dialogues with the U.S. Department of Treasury on some of the financial issues. I've reached out to the American Medical Association. I've reached out to the National Association of Realtors and the retail industry. These are examples, I think, of the groups that we have not historically engaged, but they are in the front lines. And so the more we can bring them in, and one of the things, incidentally, I'm curious to see when I get to Glasgow, is how many of those, what I call seemingly disparate communities, are actually at COP26, asking us the tough questions, and are we reaching out to them? So the first part is we need to reach out to a broader set of users and communities. The second is, I believe we need to build a much more robust service ecosystem that we do tend as technocrats to say, look at this output from CMAP, look at this wonderful product from this model, and then assume the users, whoever they may be, emergency managers, public health officials, know how to interpret and apply that information. There is an opportunity for building a sector, some of which may actually be commercial, that is directly tied with tailoring the products, providing a clear interpretation of the most skillful models, for example. And it's incumbent on us as government officials, and I'm also a political appointee, to help build that service capability, both the public aspect of it, the international public aspect of it, and the private sector component. Thank you for that question. Thank you, Devin.
Thank you, Rick. Let me actually just see if somebody else would like to provide a second view, a second answer. And I cannot see the people on the floor.
So just quickly, Detlef, we have quite a lot of questions in the room. So maybe if we go to one more speaker to respond.
Yes.
Yeah. All right, let's do that. So let me see. So let's go over here and then we'll go over there.
Thank you. Thank you, first of all, for your presentation. My name is Sébastien Richer. I'm from France. And I got a question because it was mentioned that it would be great to have better resolution in the scenarios and so on. And a better resolution means at least a quadratic number of inputs to get in there. My question is, for us who are modelizing for the IPCC and so on, and for us we are reviewing the modelization, aren't you afraid that by getting too much into the details, we are losing the capability of evaluating the models? I mean, not all of us do have the computer capabilities to deal with the scenarios, with the models and so on. So what is your input on that? Better resolution or number of contributors?
Thank you very much. Maybe I look at Veronica or Kirsten if you would like to answer.
I can make a start, yes. Thanks for the question. I think what we have heard from the various speakers and people on the panel is that the climate modeling community is seeking multiple approaches towards what you are raising here. So it's only one approach to go towards high resolution modeling, but we were hearing from several people that this could be quite limiting because of the high computational costs. So we, as Albert was saying, we need a hierarchy of models. We also need to invest in Earth system models to address things like permafrost or ice sheet melting. I also presented one possible approach that kind of bridges across these approaches, that learns from high resolution short or regional simulations together with observations, uses the improvements in machine learning to build a core scale Earth system model that has better representation, for example, of the land or of a cloud through the incorporation of machine learning observations and high resolution data. And I personally fully support what Albert said, that we need this hierarchy to address the various things. And I just before I give over to Kirsten, maybe want to also add that in the IPCC report, we have developed methods that combine observations and climate model simulations together with an improved assessment of the climate sensitivity from observations and paleo to come up with really robust projections for the IPCC report. And I think all these lines will be continued and will hopefully address the questions the climate modeling community will need to address.
Thank you, Veronica. Peter, is it okay if Kirsten comes in for a brief time?
Yeah, sure. Please go ahead. Yeah.
No, I'll just make a very quick addition to what Veronica said. I fully support everything that she said. The other piece of it, I think, is that many of these, as much as the information content in these high resolution models means that it's the data analysis capabilities must be up to the task. That there are opportunities for international databases that are accessible by external researchers as well. And I think that's one of the services that CMAP has certainly created, and WCRP more broadly has created for many of these grand initiatives in the past. So I think it is certainly, you raise a good point that that higher res means enormous quantities of data that are difficult to analyze, and it might only be happening by people who have the computing resources to tackle such a large problem. But I do think we are making efforts to make these data accessible to the larger community.
Thank you. Peter, over to you.
Yeah, okay.
Next question from the floor.
So just to let you know, Detlef, I have 3 questions lined up. If there's anybody else.
Yes. I think we can do this.
Okay, so I think we now have 5 questions lined up.
Yep.
Do you want me to take them one by one, Detlef, or should we take them 2 at a time or something?
I suggest we only have about 10 minutes left. You just take them, all 3 together, and then we will see how we answer them.
Okay, we've got 5. We'll take 3 together, and then we'll do another 2. So if you could take the 3, we've got
3 together.
Hi, I'm Richard Jones. I'm one of the coordinating lead authors of the Atlas chapter of the Working Group 1 report. I just wanted to make a comment and then a follow-up with a question on this issue of regional climate information. There were a couple of comments that were made earlier that we have a great deal of uncertainty about regional climate change, and if you look in the report, you'll find that there's a lot of really solid information on what we know has happened and what we are expecting to happen in the future on regional climate change. But the other aspect of this is that there was a statement made about we know an awful lot about what the users need at that scale, and I really don't think that's actually the case. And I think a lot more effort needs to be put into really developing the information that's required for them. And so I'm just wondering, in the context of this limited number of people that are available for these efforts, whether we should actually slightly rebalance things and put more effort into the analysis of existing simulations rather than putting more effort into building new, bigger and better and shinier climate models.
Yeah. Thank you, Richard. And just a reminder to everybody also to try to be fairly brief with your interventions.
Now the picture is frozen. I'm not sure. Can you still hear us?
Thank you very much. My name is Abdallah Muksit. I am secretary of IPCC. But I am speaking with the hat of a former meteorologist and also numerician. And I was with numerical prediction, and also I was invited by Albert because we worked a lot of time. But really look into this side events, and I was asking myself what can people take away. And I think the title was about the future of simulation and models. And we did have, the perspective from developed country, regional one, but I wanted to draw the attention from regional one. He started by saying what is concern, how to save lives and goods. It was exactly the immediate, so no warning, and also some forecast for seasonal forecast. This is what is really important. After this, we can think about future simulation. But I will say, because in Morocco, we have, to have a good computer, we have now the petaflop computer. But to run climate simulation, we should integrate the national component, because national component, you have the necessity to have a computer that should be sustained, not only to develop observation, not only this, and this is why I think developed center should help those national centers to come with this complete picture. And this is, I think, something that if you are not integrating the national component in this process, I think the whole system can collapse. And this is, I think, something that it is good for have a good collaboration to install consortiums and to come with something global. Without involvement of national and developing country, their capacity, how we can sustain their capacity, not only in the computing facilities, but also in human resources. I can give you the example, in the meteorological department in Morocco, we have 20 doctors, female, and 10, and this shows what is the necessary requirement to maintain and sustain future research in modelization. So thank you very much.
Very well, thank you. And we're going to go to one last intervention. If you could be brief, that would be excellent.
Thank you so much. This is Saeed from Oman Meteorological Department. And I have a question on, as you mentioned, that there is a high level of uncertainty associated with the climate projections. My question is, how should countries or people deal with such uncertainty to take decisions? Thank you so much.
Thank you. So over to you, Delev, to choose the respondees.
Yeah, thank you. So we have essentially three aspects here. One is the question, how many model runs do we need, as opposed to should we look more into the existing model outputs. We have the point of integrating national components, and I think this is a very valid one. And then the last one that maybe is freshest in all people's mind. And I was wondering, Greg, you're not really part of the panel, but you still might have a view on the very last point. Maybe you want to start.
Okay, thank you. So I think it's important, and Rick alluded to this earlier in his remarks. It's important to communicate uncertainty, and as scientists, that tends to be our emphasis, is to communicate uncertainty. But I think it's even more important when dealing with users and stakeholders and decision makers to communicate confidence. And what we have high confidence in a lot of the scientific results that arise from not only from climate models, but from observations, from process studies, our general understanding of how the climate system operates, why it changes, how it varies, and how it will change in the future. And the IPCC assessment reports try to convey that using this calibrated language that we apply that allows for statements with high confidence or very high confidence or virtually certain, that kind of language that allows us to try to communicate that. And I think as a community, we should be doing a better job of laying out and emphasizing those aspects in which we have confidence. The uncertainty part, of course, we have to make decisions in the face of uncertainty. There's always uncertainty, and we do that in our daily life in all sorts of applications. The insurance companies, for example, deal with uncertainty all the time, but they have systems to manage that. They do that by understanding that uncertainty and translating that into risk and how to reduce risk, how that risk changes under different circumstances. And I think that's where we can make use of the information we have about uncertainty to cast it in the form of risk, rather than it being a paralyzing thing that we can't make a decision because we don't know enough. That's a unhelpful framing, but casting it in terms of these are the risks, we have certain unknowns, but how can we ask about managing those risks, reducing those risks? How might those risks change in the future? That's where I think we have opportunities to communicate better, and I think that's something we should be focusing on. Thanks.
Thank you, Rick. Regarding the first point, and I will come back then to Kirsten and Veronica afterwards. Rowan talked about prioritization or making choices, and maybe Rowan, you can elaborate a little bit also in this respect, in this view on how much older runs we should first of all analyze and learn as opposed to run again models.
Thank you, Datlev. So, I mean, actually, I think the intervention concerning national priorities and protecting lives and livelihoods is actually really a helpful focus for us all. This is a priority for every country on the planet, and we heard about some of the work we're doing in the UK to try and better integrate our scientific capabilities to address precisely these kind of priorities. And we have to every nation needs to do that in their own way, and we have to work out also what is the role of international collaborations in making it easier for nations to do what they need to do and address problems that are beyond the resources of any particular nation. Now, early warning is, as we heard, is absolutely a priority for any country. But in addition is this issue of risk assessment. And if we could take just a really concrete example, we heard about the tropical cyclone that hit Somalia. So the question is, what was the likelihood of that? What is the likelihood of another tropical cyclone hitting Somalia in the next few years? And the truth is, we don't have the tools to answer that problem with any confidence. The models are not good enough for that particular problem. But it is an extremely important problem when we want to think about building resilience. So that's, you know, that's an example of how I think the current tools are not good enough for some very, very important issues. That isn't to say, and I agree with Greg, of course, and with Richard, that there is a lot of information where we do have, you know, robustness and confidence, and we should obviously draw on that. But we also need to be very clear that we don't have the tools to address some very important problems that are directly relevant to lives and livelihoods.
Thank you, Rowan. You did not exactly address the question I posed to you, but so I pose it now to Veronica. Given that we have CMAP 6 just completed and CMAP 5 is in the archive, what is in fact from the community the sense that how useful is still this old in quotes output? Or what's the need for running again a different model? How much in fact effort should we also encourage people to put into analyzing the existing model output?
So I think with CMAP 6, and I fully agree with what Ron just said, we have a huge, rich source that of course will be further analyzed throughout the next several years. So it's not that we are stopping to analyze. A lot of the publications are still to come. So it's not that all of CMAP 6 just ends with the publication of the IPCC 6 assessment report. So that will continue for quite a while. But at the same time, we have identified further possibilities for improvements, and there are several lines that we will follow, and these will address new problems. The demands are changing, and that's why I think both lines are definitely required, and we are going to move it forward in these ways. We will continue model development with high resolution machine learning based models and system models, all important tasks to further address the challenges we see.
Thank you very much. Peter, I have to check now with you. We have about a minute left. We can get one or two more questions, or we have to wrap up. I leave this up to you.
Right, so we're getting from the floor that we're okay with questions, so I think we can go to wrapping up, and maybe we have a quick, I think it would be very interesting to hear, wouldn't it, very briefly from everybody who's taken part. But over to you, Datlev.
Thank you very much. And so this, it is actually now, well, 4 o'clock, I guess, in the UK. I would like, first of all, to start the wrapping up by thanking all the speakers and all the panelists for the contribution. I think these were very important points that we heard, various different aspects of future climate modeling. I guess it is true that there's a lot of technical development required for the future. This is technical in the sense of model development, including more physics, including more dynamics. But in fact, given the hardware changes in the future, I think we really have to spend efforts to make the existing or the future model codes runnable on the future hardware. I think we should not forget this. Doing an exascale computing does not just come from the shelf. It's actually cutting-edge informatics science that we have to develop. On the other hand, the other part of the spectrum, I think it was really clear. I think we have to talk about a kind of a co-development of climate modeling in the future, where the users are being asked right from the beginning what they need, that this can be addressed from the results that we produce, and not here after the fact, well, it's nice to see this number, but this is not what I'm interested in. And I think all the contributions here today really spanned everything in between. And so it is clear that climate modeling will continue to play an extremely important role in the future, more jointly and merged with observations, and that maybe had been the case in the past. But it is our experiments, it's our tool, it's our exercise that we can use to really understand the climate system in the future. So I think the importance of climate modeling down to the regional and local scale, where decisions will be made, and the required information for this will grow even more than this had been the case in the past. So this is, we need to come to a close. Our time is up. And thanks again, everybody speaking, giving interventions, everybody listening. And thank you very much, and a good day and a good evening. Bye-bye.
And thank you. Yep, thank you to you, Detlef, as well. And thank you, everybody in the room. Thank you.